Okay, let's get started. If you could take a seat, thanks. Okay, so morning, everybody. We end the year as we began with a good old dose of optics. I bet you've been looking forward to this. Right, so in part one, we talked about geometric optics. This part of the course is now wave optics. So at the start of Michaelmas term now, we started off with geometric optics. We sort of used the idea of that light propagates as a wave, or in fact wavelets, just to sort of explain the idea that light could travel in straight lines. Right? That we sort of used it as a way to justify where we began, and from that we derived the law of reflection and refraction, and then the rest of geometric optics. But really this sort of wave, light propagating as a wave, was really just to sort of justify our start point, and we then kind of abandoned worrying about anything to do with the actual wave nature of light. So in this part of the course, we're actually now going to see that a large part of optics is actually, described by the wave nature of light, and the key words are going to be interference, so the superposition of two or more waves to form a resultant wave, and that leads to the concept of diffraction, so the bending of waves as they pass by some object or through some aperture. So whereas in the first part key figures were Newton and Huygens, a key figure in wave optics was Thomas Young. So this is just a book written about him entitled The Last Man Who Knew Everything. Of course, that's not true, but he did know quite a lot of things, actually. He was a very successful doctor. He worked out how colour vision worked. He worked out the mechanics of strong materials, surface tension, helped decipher Egyptian hieroglyphics, I think, and also came up with some strange new method of tuning musical instruments, right, as well as his work on wave optics. So he was quite an accomplished guy. And in 1801, he performed his now very famous two-slit experiment. I expect a lot of you will have done this at school. And you shine some sort of light on two slits, and you observe the fringe pattern from the interference of the waves coming from the two slits. So, in fact, the majority of this lecture is going to be talking about the two-slit experiment. It's even going to topple over, I think, into the next lecture. Then we're going to move on to diffraction grating. So this is basically a generalization of two slits, but to many slits. So we'll talk about the basic properties of those. This will be next week, I think. We'll get on to single slit diffraction. And then we'll briefly at the end talk a little bit about two-dimensional diffraction, in particular diffraction at a lens. Okay, so it's all about waves. Oh, by the way, I should have checked. Have you all got a set of notes? There seems to be some spare, so I imagine you've all got them. As usual, they're available on my website, and as before, there's a few places where there's some sort of boxes to fill in. I don't know if you've noticed that, but I've now, from Michaelmas term, uploaded the version where the boxes are revealed, right? So I don't know if you've noticed, but I will obviously do that for this as well, but only at some point over the holidays. So trying to encourage you to come and to follow. Okay. So it's all about waves. So you will now be quite familiar with how to describe a wave mathematically. You've been doing your waves course, but let's just remind ourselves. So this is what to fill in that box. So we're going to look at a 1D wave, and I'm going to describe the waves like this. So some sort of amplitude, and let's make it a cos. Kx minus omega t minus phi. Right, where k is the wave number, 2 pi over lambda is the wave number, and it describes how many oscillations the wave does per unit space. And omega, of course, is the angular frequency, and this describes how many oscillations the wave does as a function of time, or per unit time. And then we've got this phi, which I've just added there. It's some kind of phase, which you can have just to describe how two otherwise identical waves perhaps can still be out of phase, right? So it's some sort of arbitrary phase. Okay. You won't be surprised to know that there are other conventions in use as well, usually to do with exactly where you put the minus signs. Sometimes you might see an omega t minus kx rather than the other way around. These are just conventional. On my website, you'll see a bit of a short document just sort of outlining other conventions that you might see, but I'm going to be consistent and use this convention. Okay, so my basic wave is going to look like that. And the important thing to realise is that this is a travelling wave, right? So let's do that. I could plot it as a function of distance if I want to. Okay, oh, the other thing I was going to mention, sorry, I forgot. Mostly in this course, I'm going to be working in sort of normalised units. I'm going to basically set that to 1. That's just because most of the time what we care about is the variation of the wave as a function of space and time. I don't actually care about what is the peak amplitude, what's the peak intensity, right? So if you see some A's just being dropped or not there, don't worry, it's just because I'm working in normalised units. In principle, it is there really, right? But I'm sort of being lazy and we just don't care about that bit. Okay, so what was I going to say? Right. Yeah, so this is a travelling wave, and so after some time t, it's going to look the same as it did at t equals 0, except it's just going to have moved on a little bit, right? And specifically, it's going to look exactly the same as it did at t equals 0 when that's true. So x equals omega over kt, or we can otherwise write that as vt, because I expect by now you will be able to recognise that as the phase velocity of the wave, right? Okay. All right, so this is what we're going to work with, and of course what you've been doing mainly is learning about waves on strings, but it turns out that light waves can be described mathematically in exactly the same way, so we're going to carry on using that. Another thing that I was just going to mention as well is that this is a wave as I've drawn it, going from left to right, it's going along in the positive x direction. If I wanted to describe a wave going the other way, I would draw that. I'd stick the minus sign there in front of the kx term. That means I'm encoding the direction of the wave basically in the wave number, the direction of the wave number k. Just to give you a quick idea, just as an aside really, what you might see in books is that people might say, okay, well, clearly cos is symmetric, so I could just write that, right? And you'll see people writing this. I recommend that you don't do that, because what you've done there, of course it's true, mathematically, of course it's true, but mathematically you've just sort of, but you've lost the sort of information about what's actually going on. You've lost the underlying structure, basically. So I would choose a convention. You know, it's again all about conventions. Choose a convention, stick with it rigorously. If you've got minus signs in there, keep them in there, even if a different expression would come out mathematically the same, and then you won't get sort of muddled up, hopefully. Okay, so, right, so I've just said this bit. Yeah, so you've been learning about waves on strings. We can describe light waves in the same way. More complex versions are available for general motion, namely, maybe you don't want to assume your waves moving in the x direction, so you would replace that term by this, for example, where this is a position vector. That's a wave number vector, so it's got the magnitude of the wave number, but the direction in general of the propagation of the wave. So you might see that as well. And certainly next year, you will be using that sort of notation much more. So what's actually waving in a light wave? Well, again, you'll learn much more about this in second year electricity and magnetism, but basically it's oscillations of the electric and magnetic field, which vary in space and time, just as the motion on a string. So we can describe this mathematically in exactly the same way. Okay, so an important kind of wave in this course is going to be the plane wave. So that's just a series of parallel wavefronts just moving along together in a particular direction, right? So I could draw this, sort of try and draw this a little bit in 3D. So a plane wave, in principle, these planes are all infinite in extent, right? They've got a constant frequency or constant peak-to-peak distance, lambda, and they just move along all together. So here's a 2D slice of that, just moving across the page. Okay, so there's my plane wave. Of course, this is a three-dimensional thing, but I'm just drawing a slice here. And it would take me a long time to sort of draw that every time I wanted to represent a wave to you, so I'm not going to do that. I'm instead just going to draw on lines marking on the peaks. Those are going to be my wave fronts. And okay, if you want, you can also mark on lines perpendicular to that, the rays representing the direction of the wave, right? Just as we were doing in geometric optics, we were representing light as waves. Oh, rays, sorry, rays. Okay, so another kind of wave that is important in this course is the spherical wave. So this is what happens if you cause a plane wave to impinge upon an infinitesimally small hole, right? That's what that is. And what happens then is that afterwards, the wave kind of spreads out, roughly speaking, in all directions, right? So you get this spherical wave. Again, this is a 3D situation that's going on, but I've taken a slice of it, so this looks like a circular wave now. Right, now I said roughly speaking in all directions. We'll see in just 2 or 3 slides' time that that's not quite true. I'll qualify that a bit. And the other thing is that this sort of perfect spherical picture relies on this hole being infinitesimally small. We call it the ideal case. If you see the words ideal case in optics, it's usually, certainly in wave optics, what it's meaning is that your slits or your holes are infinitesimally small or narrow. Okay. But in a real experiment, of course, you wouldn't have an infinitesimally small hole. It would have some sort of finite size. That does have a bit of an impact. It means your wave is not quite spherical. And we'll talk about the impact of that sort of later on, not today, but later on in the lectures. Okay, a related wave is the cylindrical wave. So, of course, as a 2D slice, this looks exactly the same as what I've just drawn. But what this is coming from is now this isn't a hole, but it's an infinitesimally narrow slit, right? So it's got finite size in the sort of long direction, but infinitesimally narrow. And then you get this sort of cylindrical wave spreading out along the full length of the slit. So, as I said, in 2D, this looks exactly the same. I can't tell if I've got this, this spherical wave as I did on the slide before, or a cylindrical wave. Fortunately, due to the symmetry of these problems, it really doesn't matter. We're just going to be treating 2D slices of these things, which look like this, and we don't have to worry about the 3D structure, right? It's the same mathematics, just taking this 2D slice. Okay, and then I've said, yeah, finite size slits will be treated later, right? I'll tell you about that a bit later. Okay. So for the remainder of this course, unless I say it specifically, we're talking about slits, basically, infinitesimally narrow slits. Right, as an aside, so just as last time, everything in red means it's off syllabus. It's sort of interesting for you to know. You might come across it in books, but it's not something that is, examinable at all. But just for those who like to know about the finer details, there's something called the obliquity factor, which you may come across, you may have already seen in books. This was something that arose from Fresnel doing a much more detailed treatment of what really happens when a plane wave impinges on a hole and passes through. Right? So a few minutes ago I said the wave spreads out roughly speaking in all directions, and then I qualified that a bit and I said I'm going to explain that's not quite true. And this slide is the explanation of that. So actually what you see experimentally is that you don't get the same intensity in the forward direction as you do at the sides, and you don't get any backwards going waves either. And so this was a bit of a fudge factor, this thing called the obliquity factor. A bit of a fudge factor Fresnel put in really to try and explain that. So this theta would be 0 for a forwards going wave, it's kind of measured from the forward direction. It would be pi for a backwards going wave, and you multiply the amplitude of the wave by this factor, and so you can see how that can, describe the fact that you don't get backwards going waves, and you see less intensity at the sides and so on. Now, it turned out that this factor actually really does arrive naturally from much more rigorous mathematical treatment that was done by Kirchhoff. So it really is there, it's part of the description. But initially it was just sort of a fudge factor, as I say, that was put in to try and explain what they saw. Okay, now we're largely going to ignore this. The details are off syllabus, as I've said. It's interesting for you to know. But mostly we're going to be working in the small angle approximation, as we did in geometric optics. So this is going to be a tiny, tiny effect. And also for finite-sized slits or holes, it actually is overwhelmed by another correction as well, which I'll talk about later. So it's going to be ignored completely in what follows, but it's nice for you to sort of be aware of it. Okay, so the first interesting problem, and this is basically going to take up the rest of this lecture, is to talk about what happens at two slits. Okay, so I've got my plane wave now impinging on my two slits. These are, we're treating the ideal case at the moment, so these are infinitesimally narrow slits. And so we get these, spherical waves just emerging and overlapping each other in space. Okay, so what's going to happen, of course, is that where the waves overlap, we're going to get some kind of interference. And what we want to know, we want to sort of analyse, is where is it that these things will constructively interfere and where will they destructively interfere? That is, where will their amplitudes, where in space will their amplitudes add up and where will they sort of cancel each other out? Okay? And then we're going to have to think about the intensity, because it's actually the intensity that Ri is sensitive to. That goes as the square of the amplitude. And probably you're used to this already. You would know about energy going as the square of the amplitude. So intensity is just a measure of the energy carried by the wave. So, okay, quick run through of constructive and destructive interference. Going back to school, you will of course be extremely familiar with this for many years now. But let's just remind ourselves. So if I have two waves and they're sort of exactly lined up like this, so that the crests align and the troughs align, then we get constructive interference, right? The amplitude doubles and the intensity therefore increases by a factor of 4. And then if we have the case where they are shifted by half a wavelength, so that a crest in one exactly aligns with a trough in the other, then we get destructive interference and intensity of 0. Now, two important words or concepts for interference to actually happen is what's at the top of this slide. So I haven't defined it on the slide, but you might want to supplement what I've written there just by defining. I mean, I think you will probably all know what monochromatic means, right? But the other one you may not so much. Anyway, so that's single wavelength, right? So when we talk about interference, we mean light of the same wavelength can interfere. I will qualify that a little bit. So basically, interference happens between light of the same wavelength, but actually, light of different wavelengths does also interfere. It's just that the interference pattern washes out. It turns out to wash out so rapidly that you can't see it. At the very end of the lectures, I will do a little bit more of the mathematics of that so you can see. But at this point in the lectures, for all intents and purposes, you should just think, okay, only light of the same wavelength interferes. Okay? And then the other one is coherence. Right? Now, what that means is that the two waves, or however many waves you've got, waves must maintain a constant phase relationship. I'll explain what I mean by that in a second. Phase relationship. Right. So, is it still up the top of the slide? Oh, I've just, yeah, the phi's there anyway, or there, right. Okay, what that means is that if my waves start off out of sync, right, let's say by some phase phi, I don't want that phase to change as a function of time. I want that difference to remain constant. If that's sort of, varying, then actually your interference pattern just washes out again and you don't see any fringes, right? So what we need for interference is we need monochromatic light and we need coherent light. Okay, so let's look a bit more closely. That's what's going on at our two slits. So here we are. We've got our plane wave now coming from below. It's impinging on our two slits. It's producing these spherical waves. And what I'm interested in are these points, where the maxima, the peak amplitude in one wave exactly coincides with the peak with the other, right? So these dots mark on the positions of constructive interference. Now, I could also look at places of destructive interference as well. So I could look, for example, at let's go on one of the lines from the left-hand side, but sort of halfway between, ooh, you need a steady hand for this, sort of halfway between the other wave, and those are the points of destructive interference, which we'll get to, but for the moment we're just looking at the places of constructive interference. So let's move on in time a little bit, right? So my waves have moved on, I'm just got another one being produced here, and the others have all moved on, and then I can mark on the points of constructive interference again, right? Just marked on another set of dots. And I can carry on doing that until I get very bored. So my waves are moving on, there we are, and we see this sort of pattern sort of starting to emerge with these lines here of constructive interference. So let's clean up the diagram a little bit. There we are. So taking off the circles, but just leaving these spots, which represent our positions of constructive interference. And what you can see is that they seem to be occurring in various sort of different directions, right? They're basically on straight lines. We've got some curvature here when we're close to the slit, but as you go further away, you can see that they seem to be occurring just at various different angles. So our question is, can we actually calculate those directions without sort of our lives draining away by drawing circles and dots, right? Which I don't recommend that either I do or you do. And of course the answer is yes, there is, right? There are. Of course, there's an easy way to calculate this. So the thing to realise is that what those lines are the sets of positions at which the waves from the two slits are in phase with each other, okay? Now what we mean by that is that they should, right, so an easy one is if, hang on, I meant to go back, right, let's go back one. An easy one is where the path difference from each slit is the same length, right, and those are the positions of constructive interference where the path length for away from this slit and away from that slit doesn't differ at all, right? Zero difference, and therefore clearly you will get constructive interference. Remembering that the waves were in phase at the time of the slits, right? But in general, you also get constructive interference if the path lengths differ by some integer number of wavelengths, right? So as long as they've travelled, one wave has travelled a distance that only differs from the other one by some integer multiple of wavelengths, then you're also going to get constructive interference. Okay, now at any given point, let's go back again. If I were to just sit at a particular position here, right? Now my wave, remember this is a travelling wave, right? So the wave is travelling along these lines. So if I were to sit at any particular place, I would still see an amplitude oscillation, right? It would still be oscillating in time, but that oscillation turns out to be so rapid that the eye isn't sensitive to it. If that doesn't quite make sense yet, it will come out of the maths that we do probably at the end of this lecture or the beginning of the next. So there's going to be a term that is rapidly oscillating in time that we're just not going to care about, basically. Hopefully that will be clearer when we do the maths. Okay, right. All right, so let's see how we can actually calculate what's going on. So this is really just an illustration of what I've just said, really. So clearly we're going to get constructive interference when the optical path length is the same from each of the slits. That just lies along that straight line, halfway between the two slits and perpendicular to it, right? But in addition, I could have this sort of situation, right, where the optical path length from one of the slits differs and is longer by, let's say, one wavelength compared to the one on the right. That's also going to give me constructive interference, and so on. I could have drawn more of these where they differ in 2 wavelengths or differ in 3, and so on and so forth. So let's just cut the diagram down to the basics and see how we calculate that. So here I've just sort of made it the same thing but a bit more clear. So here the blue line and the green line have the same length, and then the red is just 1 wavelength long. Right, so we want to calculate the positions basically at which this occurs. So let's draw a diagram that just looks a bit more like the experiment we're actually conducting. Okay, so here, so what you tend to do with young slits is you have your 2 slits, obviously. You have some sort of light source that you illuminate these slits with, and then you tend to observe the fringe pattern on some sort of distant screen. Okay, so the geometry of what we've got going on here is that here's my two slits separated by a distance which I'm going to call little d, and then I've got a screen over here that I'm going to look at to see the fringes, which is a distance big D away, and big D is supposed to be much, much bigger than any other distance in the problem, so it's supposed to be much, much bigger than little d. I would agree that on this particular diagram it's maybe not, not quite big enough, but I needed to fit it onto one slide. So try and imagine that this screen is, off the right-hand side of this slide by a long way, and try and envisage what these lines would look like in that case. We're going to draw it in a minute anyway, of course. Okay, now, so these blue lines are the things that we're actually interested in. These are representing, so the thick blue lines are representing the optical path length from each of the slits. And then we're saying, okay, I'm going to observe what happens at a particular point on my screen, a distance y above this dash line, and that dash line is simply the midpoint between the slits. Okay, it's just a sort of construction line to help us define an origin here. Right, what else is going on? Okay, this thinner blue line is just a construction line as well. It is the point from the midpoint of the slits that meets up at the same position here as my two, as the point that I'm observing basically. And then I'm saying that line makes an angle theta with this horizontal. Okay. So that means, just from the geometry of what you're seeing now, I'm writing this, but it is on the slide anyway. It's just that it's going to be useful in a minute, so I want it on the board here as well. Okay, so that means that tan theta is y over d, and as long as d is very, very large, which is what I'm saying we're working in that regime, then I can also say that that is approximately theta, right? And it's also approximately sine theta, which will be useful in a minute. Right, so we're working as usual in the small angle approximation due to the distance d being very, very large. Okay, so let's just sort of zoom in on this a little bit to just draw the diagram in a way that we can sort of understand why the small angle approximation works. So here are my two slits. These are my, sorry, I'll try and get out of the way. These are my sort of optical path lengths, and now I really am imagining that my distance d is very far away, because hopefully what you can see is that if this point was way, way off, off to the right or something, these lines would start, these thick blue lines would basically be parallel to each other, right? And so we get a situation that looks like that. So I've got d here. Big D is way off, somewhere like that. I had this angle theta, right? That's supposed to be the dash line marking on the midpoint, and I could draw another construction line, which is also parallel to the others. That was theta. But of course, if these lines are parallel, then also that is theta, and also that is theta, right? Now, then from the geometry, I can draw a line that's perpendicular, right? Can you see this? Okay. So I can drop a line that's perpendicular from that slit to, so it's perpendicular from this optical path length, and it's just going to meet this slit there. Now, hopefully, you can see that from the geometry, that angle is also theta. Okay, if that's theta, that's 90 minus theta, and so in there is theta. Right, okay, we're getting somewhere. So that means that, right, so my lines are essentially parallel to each other, but this bottom one is longer by some distance, and we want to know how much longer. And from the geometry of this, we can see that, okay, it's longer by an amount, delta, which I can write as d sine theta. This, by the way, is what you're supposed to be drawing in this box. I didn't say that explicitly. So just copy this diagram and essentially draw that. And this is going to be key for where we're going in a minute. Right, this is the length. I'm going to write that bigger as well. So the path difference between the optical path length from one slit to the other is given by that. And that's the thing that we want to know. Is it a wavelength difference? If it is a wavelength difference, we know we're going to get constructive interference. If it's half a wavelength difference, we're going to get destructive interference, and so on. Right? So that's what's going to be illustrated on this next slide. So let's look at what we would actually see on our screen. So this is supposed to be the screen here. I haven't marked on the slits, but this point is still the sort of same construction line that's coming from the midpoint between the slits. So what we're saying is that a point on the screen here clearly represents where my optical path lengths have been the same coming from each of the two slits, so I'm going to get constructive interference. Then we want to know where's my next position of constructive interference, or indeed where are any of these positions of constructive interference. Right. So, right. So for the box on this slide, there's quite a few things to write here, so you may, I think I want you to write, so you might want to supplement it or use the previous box. Right, so what we're saying is that we get bright fringes. I'm going to switch to white, sorry, didn't mean to use yellow. Bright fringes when this delta, this path difference that I've just given you an expression for up there, is an integer number of wavelengths long. So n can be 0, it could have 0 difference, or it could be plus or minus 1, plus or minus 2, some integer, right? So that's when you're going to get bright fringes. So that means that this delta for a bright fringe, we need d sine theta to equal n lambda. And remember from this slide, we also know that we can write sine theta as approximately theta, which is approximately y over d. So that equals little d y over big D. Right. So what that means is that we expect to see fringes on our screen when y equals n lambda big D over little d, right? So we've calculated where on the screen we expect to see constructive interference, we expect to see bright patches. Okay, we could also say, right, I'm going to see dark fringes halfway in between. So dark fringes are going to be when delta equals n plus a half lambda, which equals dy over big D. And so y equals n plus a half lambda big D over little d. Box that. Separate it from the line above. Right. Okay. So that's when you're going to see destructive interference. And then there's maybe one other thing to notice as well, in that you won't get an infinite load of fringes. There is going to be a maximum order at which you see fringes, and that is because we see bright fringes. So bright fringes when n lambda equals d sine theta, but of course we know sine theta has to be less than or equal to 1. And that's going to imply then that n is less than or equal to d over lambda. Right? So you're going to see, so number of fringes that you will see. Number of fringes is going to be 2 n max plus 1. That's the central fringe. And then you're going to see two lots of maximum value of n, one set either side. Right. So what we've basically sort of proven by making this approximation that we're a large distance away anyway, we're always going to work at large distances in this course so that we can make these small angle approximations, otherwise the math gets crazy. But what we've shown is where we can find the positions of the bright fringes. We've shown the position of where we can see the dark fringes. And I kind of, on this diagram, kind of, smoothly joined it up in between because I'm going to expect the intensity to vary something like this. But I've not actually proven that yet. We will prove it, right? We will prove the shape and do the full derivation for the shape. But I've not done that yet. We just know our positions of maxima and minima right now. Okay, so an interesting thing to do might be to say, well, can I actually separate these fringes? Can I distinguish them? Let's take some typical numbers. So I'm expecting the distance between two consecutive fringes to be lambda big D over D. So let's take some typical numbers which I've put on the bottom there. For example, so if lambda was 500, a green light or something, right, 500 nanometers, take our screen distance as 1 meter, and our slit separation of what, 1 millimeter, 1 times 10 to the minus 3, so that's 5 times 10 to the minus 7, 5 times 10 to the minus 4 meters, right? So 0.5 millimeters. Okay, can I discriminate that? Well, yes, probably just about, but I could do better if I wanted to by making my screen even further away, right? Or working at longer wavelength light, or making the distance between my slits smaller, right? You can sort of control your experiment by doing those kinds of things. Right, now, one thing that some people sometimes find a little bit unhappy, or are a little bit unhappy with, sorry, is this idea that we started off by with this diagram, right? And then I drew a diagram that seems, it was just at the top there, where suddenly I made these lines parallel, right? And hopefully you can see that that is the case when you take D to be very large, that is what would happen. But then the whole of the maths after that relied on that these lines were parallel. Sometimes people are a little bit unhappy with that. So we're going to do it in a different way. And you will not need to reproduce what we're going to do now. Not that it's difficult, but you won't need to. You will be fine in an exam to just say, right, large distances, my lines are parallel, right, and do this proof in an exam. However, sometimes people like to see this alternative proof to see that the answer pops out in another way, right? So now we're not going to, at least from the start, we're not going to assume my lines are parallel. We're actually going to work out the path difference properly, but then just do a Taylor expansion and take the limit of large D in a minute, right? So that's the thing we're going to calculate according to the geometry that's here. So this x1 is my path difference from the first slit, x2 path difference from the second slit. So let me just write down expressions for these things. So I've got d squared plus y minus d over 2 squared to the half, and x2 similarly, d squared plus y plus d over 2 squared to the half, and I want to take the difference. Okay, you're right over there. I can hear some. Anyone got a question? Are you okay? Okay. So x2 minus x1 equals. I'm going to take the d's out as well immediately out of the bracket. So I've got 1 plus y minus d over 2 squared over d squared to the half minus d 1 plus y plus d over 2 squared over big D squared to the half. And we're just going to Taylor expand that to the first term. So I've got d 1 plus a half y minus d over 2 squared over d squared plus dot 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 minus d 1 plus a half y plus d over 2 squared over big D squared plus dot dot dot. Okay, so those terms clearly are going to cancel. So I've got half, let's expand. Let's put the d squared down there. Right, and then expand those squared terms. So plus d squared over 4 oh, I know what I've done wrong. I'm going to get minus what I meant to. I meant to do x2 minus x1, but I've actually done x1 minus x2. Can everybody see that? Sorry. So let's just put a minus in front of everything, if you don't mind. That makes it easy. Minus, there we go. Right. So that will give me a plus yd over yd. Yeah, yd. Minus y squared minus d squared over 4 minus yd. Ooh, I think I've not made a mistake, I hope. If you do spot a mistake, let me know. I have made a mistake because I feel like I should have a d in front. Yes, I should. I should have another d, shouldn't I? So I've got 1 over 2d, 2 lots of yd. Right. So that means I've got y d over d. And that is exactly the expression we had before, just by not assuming it's parallel to begin with, but just taking the limit, right? So if you're happier with that proof, then great. But I think once you've seen it once, you go on and just say, right, my lines are parallel. I'm going to do the geometry with that. Okay, so just a brief aside. There's a number of different experiments which are basically two-slit experiments. And you may have had some happy hours in the lab doing Lloyd's mirror. As I see some expressions. So this is a variation on the theme, right? This is a two-slit experiment, but actually it works better, or it works more easily anyway than the traditional two-slit experiment. In fact, there's even some people that believe that Thomas Young could not have seen what he said he saw, actually, because the traditional two-slit experiment is actually quite difficult. It's kind of easy-ish these days because we have lasers and stuff, and that gives you an immediate monochromatic and coherent source that's off the board somewhere, but I said those were the conditions. You know, kind of easy these days, but he wouldn't have had that. And there are various reasons why people think that he couldn't really have seen what he said he did, and yet he actually got the formulation correct anyway. So maybe that just speaks for how good a physicist he was. Okay, but there are some variations which do work better, Lloyd's mirror being one of them, and there are other variations as well. You'll see Fresnel's mirror, Fresnel's biprism. But what Lloyd's mirror does, why it's quite good, is that it actually only uses one source and a mirror. Right, so here's your sort of source. So rather than having to have two sources and making sure they're coherent and monochromatic, you just have one. So it's naturally coherent, naturally monochromatic. It's naturally in phase with itself. And then there's some light going straight across and some light bouncing off the mirror. And so what you're really seeing is the interference pattern from the source itself plus its virtual image, basically. And so you've got this natural, coherent, monochromatic sources going on. You might remember a little bit of a complication in that you actually see the central fringe, or the first fringe, is actually dark rather than light. That's because you get a phase change at on reflection of the mirror. You'll learn more about that next year. Anyway, so that's just to highlight that. Okay, and let's just spend a little bit of time in the remaining sort of 5-ish minutes that we have talking about some practicalities. So let's see if my lasers will actually work. I'm going to actually show you first of all. Now I think we do. That's a 2. Yeah, maybe I'll go to a 3. It's not dark enough today, is it? It's not actually very dark. Maybe no, anyway. Okay, I'm going to try and show you some Young's slits fringes. Let's see. So I'll go for this small one. Right. Now, can you see? Let me put it over there a bit. Can you see? Well, where's it gone? Ha! Can you see it? Yes? So near the front of the thing. You may have expected it to be more spectacular, I don't know. But anyway, that's Young slits fringes. And actually, can people see it? Is it because it's reflecting on my nose? This happened before. Do you know, this happened a few years ago, and everyone started laughing, and I was like, oh, I didn't know what was up. And in the end, I asked my tutorial group, why was everyone laughing at me? And they were like, oh, you look like Rudolph. So if that's what, so if that's what's just happened again, I apologise, drat it. Okay. Anyway, hopefully, look at me, look at the ceiling, right? Okay. So that was Young's slits. Now, what I didn't show, and actually maybe I should have. Perhaps I should have, and I'll try and get it not to bounce off my nose this time, right, is that you can actually see it, right, now I'm showing it on the board, right? I could show it, somewhere else if I wanted to, on the wall. Anyway, it's not working too well, but I need more batteries for my laser. But anyway, the point is, I can actually form interference fringes wherever I want. It's not like an image where, the lens forms an image in a particular location. I can actually form these interference fringes, anywhere far away, close by. If I do it far away, as we've seen from the math here, then I'll get sort of more widely spaced fringes. So it's not an image. I can actually form it anywhere, but kind of control how easy it is for me to distinguish between different fringes by making them further away, or by making the slit separation smaller. That will also spread out the fringes and so on. The problem is if you make them further away so that you can actually discriminate them better, they're further away from each other, then they lose some brightness as well, right? Because the light is spreading out in space. So that's one sort of practicality, sort of complication, as it were. Another complication is that we have assumed that the slits are acting as point sources. That is, they are infinitesimally narrow. That's what you need to get this ideal fringe pattern that we're talking about. One thing, so it's related to this, and I'm going to do the lights down again. I'm going to stand out of the way. So, right, now, you'll notice that it actually looks somewhat brighter in the middle than it does at the edges, right? Now, if we were in the ideal case, that would not be true. We would see equal brightness all the way along. So that difference in brightness, the sort of drop in intensity as you go out, is purely to do with the fact that you don't have ideal slits. They are not infinitesimally narrow. They actually have some finite width, and I will, as promised, discuss that in more detail in a later lecture. But what it means is that our treatment is relying on this ideal case of infinitesimally narrow slits, and if you really had infinitesimally narrow slits, I don't know about you, but I don't think much light would get through, right? So your fringes become dim, and you can't see them as well. So that's a bit of a problem as well. So we'll come back to this idea of that as the slits get broader, the outer fringes become less intense. We'll come back to it, but the imperfection there does actually have quite a useful thing in that it allows the central fringe to be identified, right? We could easily see which was the central fringe there because it was the brightest. That can be a useful thing. Right, something else is that Young's slits assume that a plane wave is being used for illumination. Right, so it assumes that what you've got impinging on your slits are these plane waves. Well, how do you actually produce those plane waves in the first place? That's a bit of a practical issue, right? So all these things are together are why people thought that actually Young probably didn't see what he said he saw. Well, one way of doing it is, I might just rub that out so I've got more space. One way of doing it is to use a point-like light source, right? Now that's going to have then perfectly sort of spherical waves produced, but if you then go far enough away, that will eventually become the plane waves that you want, right? So that's sort of traditionally what's done. You have a very small source, you look at it, you put your slits quite far away so that you've basically got plane waves. But again, that's an issue. If you've got a point source, not producing very much light anyway, if then you also allow that light to spread out for a long way, it's even more dim here. So things get very sort of faint, and that's not ideal. So a better way to do it is to realise that the plane waves that you want are actually just parallel rays, right? So plane wave, that's a plane wave. Well, how do you produce parallel rays? Well, you know from the geometric optics course that what you could do is use a lens. So you could put your point source at the focal point of the lens, use a lens to then produce your parallel rays, i.e. plane waves, right? And then you don't have to be very far away from the slits themselves. You can get brighter fringes. However, you've still got a point source here, right? So it's still not producing masses of light, Also, you can actually use a lens the other side if you want to as well, to sort of so that you don't have to have your screen so far away, and that also solves a little bit of the problem of brightness on the other side as well. Okay, now why do you have to use a point source? Why could you not use a bigger source of light? I think that was what I've just said on the lens, right? Why could you not use a bigger source of light? What's the issue? Well, that's to do with the coherence argument that I talked about, that you need this constant phase relationship between your two sources. Now, this is supposed to be an extended source of light, right? Let's say we had one. Well, the light's like essentially produced by, electron transitions sort of all over the source, right? And so you've got photons coming out. And if you had an extended source, there's absolutely no reason why light produced from some point up here in the source is coherent with another point down there, right? So if you have a too big source, essentially, there's no reason why the light going to the different sources would actually be in phase with each other, and your interference pattern washes out. We'll talk a little bit more about that just at the very end. We'll just touch upon it. Okay, so what else was I going to say? Yeah, now, okay, then the question might arise, well, how small does your source need to be? Because, again, doing a perfectly point source is quite difficult. Well, it turns out that it doesn't need to be exactly a point, but as long as it's small compared to any other distance in the problem, then, again, you're okay, and you will get interference. Okay, 2 more slides. I think I can do them very quickly, so we'll do this and finish. Okay, so all of this has assumed monochromatic, a monochromatic light source, as I said, and I also said that light of different colours doesn't interfere, and then I qualified that by saying that's not quite true. It does, but the pattern just washes out. We will address that at the end. Again, I say for your purposes right now, for your understanding, just think of it as that the light of different colours does not interfere. So what happens if you have different colours in your light source is that you will get separate fringe patterns produced from the different colours that are in the light, right? So this is what things might look like if you have white light, which I'm broadly saying consists of blue, green and red, right? Because blue has a smaller wavelength, and we have our formula for fringe separation up here, right? So if you have smaller wavelength, you've got smaller fringe separation, and we go to green and then red, which is here the largest wavelength, so the largest fringe separation. And each of these is a pattern in its own right, a fringe pattern in its own right of a different colour, and they just superpose on each other, right? So they will only interfere with themselves, blue with blue, green with green, red with red, and then this is your resultant pattern because all of these fringes are now just overlaid, right? So you'll get a nice white fringe in the middle, but then quite a complex pattern of colours as you go out. Does, of course, make the central fringe quite easy to identify because it's the only bright white one, but it's a bit difficult to know what else is going on. Okay, that's a good time to finish, so I will see you again tomorrow. Thank you very much. Do you mind if I take these? I've got for tomorrow I might need them. Thank you.